Okay, let's start again. Welcome back. Before we start, it's sure that tomorrow we're gonna do this hands-on session. So Costantino is sending Nicolao in the web link for the Git repository. So there are some files, Costantino lectures as well, but also some Mathematica notebooks that we're gonna use tomorrow. So if you can download and then start playing, in the sense, at least checking that the notebook works on your laptop. I mean, it would be nice, so we can do something together. Okay. Let's finish what we started yesterday. So we want to understand, or at least sketch, what's the strategy to compute, to describe tidal effects, and actually to describe the effects of a tidal field on top of a, well, for us is a neutron star, a star. Well, you can use the same equation, and we'll actually check this for like computing the response of a black hole or something different, but the strategy will always be the same. So just to remember that the goal of today is to compute actually these objects. Actually, in the first lecture we're gonna see how to compute these, so the radius of a neutron star, and then the final goal is to compute the log number K2 with which you can derive the tidal deformability. As we have seen yesterday, this tidal deformability is the parameter that enters the gravitational waveform. And just a reminder, as a summary of yesterday, there is an infinite number of these guys. Okay, both these are the mass log numbers. There are also the electric ones, and we're gonna focus only on this, which is the L equal to quadrupolar log number, which is the largest in magnitude and also provide the leading order contribution to the waveform. Okay, so this is gonna be the most important quantity that we're gonna consider. So the strategy, as I was telling you, to compute that thing is to do again perturbation. This time we're gonna do perturbation on a background which is not the flat space-time that we have considered, and but I'm gonna consider a background G mu nu which is encoded in this line element. In coordinates tr, theta, phi. So I'm assuming that my G mu nu 0 describe a spherically symmetric, static stationary background. As we discussed the last time, in principle, I mean, you can compute even everything on top of a non-static background. So if you want to describe like a rotating neutron star, everything will be extremely more complex, but there are already results in literature about this. So this is the line element. This is the usual 2D solid angle. So this is r squared, the theta square plus the phi square sin theta square. And this function n and f, nu and f, are function of the radial coordinate only. So what we want to find, first of all, is to determine the G alpha beta 0. So the first thing that we want to determine is the background, and in particular the form of nu r and f of r there, which of course in vacuum corresponds to the usual Schwarzschild limit. So in vacuum, E to nu and E to f are 1 minus 2m over r and 1 divided by 1 minus 2m over r. I want to understand what's happening when the Einstein equations are not vacuum, but there is a stress energy tensor, a background stress energy tensor, that is of this form. So I will not write this anymore, I mean, again, at the blackboard, but when we start discussing about perturbation theory, I mean, we said that, I mean, if you take the whole package of the Einstein equation, there will be like this, the basically geometric part, the Einstein tensor on the left, and on the right-hand side, we will have like the stress energy tensor, and for now, we are focusing on the background. So before perturbing everything, we have a background stress energy tensor, which is given by this, that's gonna describe our the internal composition of the star. So this u mu is the force velocity of the fluid element. This is just the x mu in the tau, tau is the proper time. And then you have the epsilon and p, which has the energy density and the pressure measured in a local inertial observer at rest with the fluid element. Now, in the Newtonian limit, epsilon basically is the mass density times chi squared. And also, I mean, for general matter, sorry, P, the pressure is always smaller than the energy density for standard matter. These two variables actually are not independent, and indeed, in the exercise that we're also going to find, that we're going to do tomorrow, we're going to show how they are related, but basically, P and epsilon are related by an equation of state. An equation of state is just a microphysical relation between these two quantities, and for the sake of simplicity and because at least for binary neutron star evolution, the one that we describe in the spiral phase, this is a reliable approximation, we will assume to have this form for the equation of state. So this is a barotropic equation of state. Not sure if there is a Y or any, but basically in which the pressure only depends on the density, okay? These models, like what we call cold equation of cold neutron stars, so neutron star that we expect at the end point of the evolution before the merger. Now, cold doesn't mean that the objects are actually at zero temperature. It just means that the temperature is not dictated by thermal fluctuation, but by quantum fluctuation. So the Fermi temperature is much larger than the actual temperature of the star. Okay, like I guess the thermal effects are of the order of 10 to 7 Kelvin, probably a bit more, and the Fermi energy corresponds to 10 to 11 Kelvin. Okay. So they are dominated by quantum effects. Sorry? Yeah, I mean, like a gas of degenerate particles. I mean, depending on the layer, but yeah, that's the okay, so we're gonna need this, and the code that I will provide you, we're gonna solve all the equations for assuming like a realistic equation of state. When I say realistic equation of state, it means computed by based on microphysical calculation. So you go to a nuclear physicist and you ask him to derive or to give a model of strong interactions that basically describe what we saw at the first slide, so the interior of a neutron star up to 10 times the nuclear saturation density. There are different models. If you remember, this different models correspond to different curves in the mass radius diagram, and you're going to find several of those, and so you can integrate the equation. But a simple barotropic equation of state is also a usual polytropic equation of state, something of this kind. where which basically the equation is dictated by the polytropic index and the polytropic constant. Okay? The exercise that we're going to do tomorrow will take care of both of them. Okay. Now, these are all the ingredients on the table. What we want to do is solve this. Okay, how do we do? So the first thing, let's express the four velocity components in terms of the background metric. And we can do this because, as I said, we are assuming like to be in a reference frame at rest with the fluid, so u mu is only like the zero component. And given the orthonormality condition, if you solve this equation as at the background, so you basically expand this, you plug u mu, you just get this is like u0 square g00. So this equation gives, what is it? This for the four velocity component. And of course you can immediately compute the components with the lower indices, and this is again G00 U0, which is plus. Okay, now we can plug this inside the 0, the stress energy tensor components, and if you expand u mu, the g mu 0, you find that the only non-vanishing components are these. I've just replaced the values of the four velocity and of the background metric inside the stress energy tensor. We're also need the components with both indices up. So if you just use the metric tensor, the background metric to raise the indices, we're going to find that this is the non-vanishing components are these. Okay. Now, we can use the Einstein equation to find now a solution for f and nu, but before this, we can take some little help for the covariant derivative of the stress energy tensor. So we, together with the Einstein equation, we also have T mu nu semicolon nu equal to 0. The semicolon is the usual covariant derivative. And if you expand this will be equal to this. I just want to give you the strategy. We don't need to go step by step because it's bluntly useless to make all the calculation on the blackboard. Okay, so we use the covariant derivative of the stress energy tensor. These basically are 4 equations. We don't need all of them. And the key point is that we know T mu nu. We should understand now which are the components that we need of the Christoffel symbols here. And if you compute all the Christoffel symbols, tomorrow I'm gonna give you, like in the mathematics, a very small function that I wrote that basically you give any metric and it computes all the components of the Christoffel symbols. And the only thing that is relevant for us is when mu is equal to R. So what we need, the only equation that we will need are those with these components. So basically we need to find what's the expression of this. dr minus g t So for us, since mu for us must be R, considering the values of t that we have, which are the only one non-vanishing, this sets up also like t mu, the only non-vanishing component is t00, so everything basically is locked. Okay? So this is the only thing that we need to take care. We know the various components of the stress energy tensor. We have written them on the blackboard. So you compute the Christoffel symbols by hand or with some code. We're going to do this tomorrow. And if you plug all the expression there together with the metric determinant, there's nothing particularly interesting if we develop this like sum and multiplication on the blackboard. But what you find is an equation for the metric function nu. So if you just plug the values of the Christoffel symbol in that equation and those values of T mu nu, what you find is this, that basically the derivative of the G00 component of the metric tensor is dictated or is proportional to the gradient of the pressure multiplied by this factor, 1 divided by epsilon plus p. Now, this is one of the equations that we need to solve the background system. And let's put it there. Okay, now we can take the Einstein equations. We have way more equations than unknown variables, so you don't need all of them. I just want to show you the relevant one. So the first one is G00, and if you compute the G00 part, which I get is equal to this, I'm using geometric units, so I'm setting capital G, so the Newton constant, and the speed of light equal to 1, just for simplicity. So this equation here will give this equation. Let's call it equation 1. Then we have the GRR, which is equal to 8 pi TRR, which gives us this equation. I think this is the only thing that we need. Yeah. These are basically the only two equations that we are interested in. Now, if you look at the structure of this equation, we can put everything in a more comfortable and a very Newtonian fashion like if we define a function m of r, which is 1 over 2 r1 minus e2 minus f, which is basically this guy entering here. And from this also, let me so I define this quantity that I call m of r, and which is this factor here. And I mean, if you invert these, you find that e2 minus f is equal to 1 minus 2 m of r divided by r. Then, if you plug, you see, this expression between brackets is exactly this guy there. So this is actually 2m over r, right? So this object here is twice m over r. So from this equation, I can simplify e2 nu and e2 nu here. And this equation here, with this definition, will become dm of r divided by r equal to 4 pi epsilon r squared. And this is, I mean, I think that you can recognize that this is a generalization of the mass equation, that the stellar structure equation which determine the mass in a Newtonian context, in which instead of having like the energy density, you have like the mass density. And finally, from the second equation, that in which we have d nu of r, and using the same definition of m of r that we have here. So if you again, you plug this definition of m of r inside the second equation, inside the g capital GRR component, we find this equation here. Or, let me simplify it. This equation becomes d nu in dr is equal to twice m of r plus 4 pi p r cubic divided by r minus 2 m of r. So the three fundamental equations that we need to P, the pressure. So the m of dr gives basically the total mass enclosed. M of r is basically corresponds to the mass enclosed in a sphere of radius small r. So if you integrate that up to the neutron star border, you find the total mass of the system. Then this d nu of r gives the G00 component, and m of r is also connected to the definition that we have seen before, to the GRR component. This equation has a very interesting property that if we take the Newtonian limit, for which the pressure is much smaller than the density, this equation here becomes like this. So in the Newtonian limit, basically, this guy here reduces to mu of m of r divided by r squared. Why this is nice? Because we haven't done this, but in the Newtonian limit, G00, that for us is E to nu, must basically give the Newtonian potential, such that basically Einstein equation gives back you the Poisson equation, okay? So in this limit, this is 1 plus 2 phi over c squared, where phi is really the gravitational potential that we've also seen yesterday. So this is basically R. So if you equate that equation with this basically tells that d phi so this equation that we found from Einstein equation in the Newtonian context, where the pressure is much smaller than the density, and all these equations reduce just to this factor. So this equal to this. Knowing also that in the Newtonian limit, the G00 component of the metric just reduced to, well, 1 plus the gravitational Newtonian potential. Basically, this equation gives you this. Now, this is the gradient of the potential, so the force. And so basically, this just equation tells you that the force acting on the element is just proportional to the mass enclosed in a sphere of radius r. Okay, so this is basically a generalization of, if you want to see this in a very Newtonian, this thing here is basically this, okay? The force per unit mass given by this. So in the Newtonian limit, we just recover the classical equation for the stellar structure that, I don't know, determines, for example, like stars are white dwarf. But there is an interesting piece that general relativity tells you, is that together with something that has the correct Newtonian limit, there is an extra contribution given by the pressure. So, and this is an effect of GR, and that because the pressure contributes to the gravitational potential because it gravitates, which is different from the Newtonian limit. So unlike Newtonian gravity, here the generalization of the gravitational potential will not only be given by the mass component, but they will have an extra contribution given by by the pressure. And indeed, I mean, at the end, this P is, if you look how it's defined in the stress energy tensor, it's basically the same dimension of a density. So this density multiplied by r's cube, this is really just an effective mass. Okay, so this thing here has the dimension of an effective mass. It's like density times volume. Okay, so these equations here that we have written are commonly known in literature as T of V equations. By the name of the people that Tolman, Oppenheimer, Volkov. I think that there are mistakes in every name that I've written here, but okay. These are the three people that contributed to deriving basically these sets of equations, which again, you generalize the equation of the stellar structure that you find in Newtonian gravity. If you want to solve this, and we're going to do this tomorrow practically, you have to give initial condition for so you basically, what we do is you have your star, and I integrate this equation from, for now, let's call it 0, the center, up to the radius of the star. Now, you may ask where this radius is located, and indeed this is a tricky point of the integration, but basically what you do is that you integrate this equation with the initial condition, let's say m0 equal to something, that we're going to find tomorrow, and you integrate that up to the radius where you assume that m of r corresponds to the mass of the star, and p of r is equal to 0. So at the boundary where there is vacuum, you assume that the pressure vanishes, where r is the radius of the star, and m is the total mass enclosed within the star. To this, you actually have to specify P0, which is the values of the pressure here. And then everything will be automatically linked together, because the equation of state that you specify at the beginning will give epsilon in terms of P0. You specify this, you have to specify, of course, nu, and there is a way, and then you can just integrate freely. And it actually, for a realistic equation of state, so the one which are tabulated, as I told you, so not polytropic one, everything basically, even M0 will just be controlled by the central pressure, so you just have to specify only one parameter to find the mass and the radius of the star in the plot that I showed you before. So each of the points that we have seen many times at the blackboard on this mass radius diagram correspond to a particular value of the central pressure that I choose here, which basically gives a particular stellar configuration. All of these that we have seen yesterday are like different values of different choices of the central pressure. Okay, different choices means larger or smaller values of the initial pressure, which then will dictate the full structure of the star. Okay, this solves basically the background that we need to perturb. So we will assume that the metric in the background, so G mu nu 0, is fully determined in a numerical setup. So we don't know, we only know the metric analytically here, where G mu nu approaches the Schwarzschild limit, so G00 and GRR will be determined by the Schwarzschild components. Okay, what we want to do now is find a way to compute H mu nu, again, numerically. And as we have done for the gravitational wave, we are working a perturbative setup, so we are assuming that our H mu nu is smaller than the background, and we have to compute perturbation on top of the background stress energy tensor, so we will also assume that the perturbations will be smaller than our background. We don't need this anymore. So how do we do it? So we have the stress energy tensor defined in terms, the background, in terms of the fluid velocity and the matter components. Okay, so the energy and the pressure, we need to perturb all of them. Okay, and consider like then a final form of delta t, which contains only linear term in the products. What I'm saying is that we need to perturb everything. Then we'll have like multiplication, and of course we'll also have G, which is G mu nu 0 plus H. Stress energy tensor is a product of things, product of these things. We need to expand all quantities and then keep only linear terms in H, delta U, delta P, and delta epsilon. And so the delta T mu nu will be given by this form here. Yeah, that's it. So each piece of this contains something which is at the background, G minus 0, P, and a linear term in the perturbation, either of the matter, the fluid velocity, or the metric sign. This delta, what I call delta U, the special components are just, can be defined as the psi k, so the spatial components of this vector, and this psi is the spatial displacement of the fluid. So you have the fluid, it gets deformed because of the effect of the perturbation, and you have like a spatial displacement which is given by this psi k. So this is the right-hand side of the Einstein equation. So basically now what we want to do is to solve this. So we want to solve H, and this is the operator that gives me the linear perturbation of the sourced by those things there. The last thing that I want to mention is that yesterday we made all the discussion about assuming a stationary tidal field, that this was a reliable approximation when you're far from the source, from the merger, and basically because there's a decoupling of scale, and blah, blah, blah. So our tidal field was independent of time. Now, the fact that the tidal field in our approximation is independent of time also means that all the perturbation will actually be independent of time. And so basically this all perturbation here, both at the level of the metric and the matter variable, will only be, so perturbations will only be defined in terms of r, theta, and phi variables. This is an incredibly large simplification, because basically it simplifies a lot the field equation. Tomorrow, actually, in the last part, I'm going to give you just an example, not at the blackboard. I'm just going to show you a case where this is not this approximation, not that, I mean, in which you have to include the time component, and which is the quasi-normal mode of a black hole, and equation becomes, I mean, a bit more complex. And in particular, for tidal effects, you can do it, and well, I think that Leonardo can confirm that there are people trying to attempt to solve this problem, removing the assumption of having a tidal field which is independent of time. This will give you actually a more faithful representation of tidal interaction in binary, because basically there is a part of ongoing research which is devoted to study what happens if this the log number, the tidal deformability, which we are assuming to be constant because the tidal field is constant, instead depends on time. Okay, and this basically doing this kind of very easy map, so transforming like tidal effect into something which depends on time, means among many things relaxing this assumption, so making all the perturbation time dependent, and this is well, at the moment, an unsolved problems, I would say. Okay, people are working on this. Okay, since you want, I think we can do like the break now, in a few minutes, and then, because what we have done is that we have expanded this guy here in terms of the perturbation. Now, what I want to give you is how to treat perturbation of this object there, and then which are the basic equations which relate the left and right hand side, and compute and solve these equations in order to find an explicit form for the metric. Okay? If you have any question, you can ask me or in the 5 minutes.
The equation of state, right?
Sorry?
The equation of state.
So,
to relate delta rho and delta epsilon.
yeah.
Delta p and
Yeah.
Okay. Yeah. And for the Gemini nu, so it's basically gonna be the square box h nu plus the term we neglected last time, right? Which was delta r times.
Yeah, I'm not gonna go in that detail. I'm just gonna go but in general, yes. I mean, in that case, you can have a box H plus something which is proportional Riemann tensor, and
Yeah.
esatto, come diciamo io, one important. Perché avevo fatto vedere quel piccolo coso, perché questa roba viene fuori da, non mi ricordo il nome, come si chiama, però un geofisico inglese del 1900 chiamato Love di cognome. Sì, fine 800. No, c'ho l'articolo originale, infatti, e ovviamente fotocopiato. Sì.
Però è una persona.
Sì, è una persona che studiava, era più interessato alle formazioni dei pianeti o degli asteroidi nel sistema solare.
Detto questo, tutti quelli che fanno lavori su questo argomento...
Sì, ormai hanno giocato, cioè noi in primis, devo dire.
Di parole mi dico che si abbondano.
Sì, con la libreria. Infatti fino a lì era tutto, diciamo, scientificamente accurato.
Una volta è venuto Chip Thorne, Torino, ha fatto un seminario pubblico che trovava queste slide, che l'ho detto all'inizio, o delle slide che parlavano della fisica del film, o delle slide in cui, a seconda del simbolino che c'era in alto, significava questo è basato su scienza, diciamo, chiara,
bello,
e questa è un po' speculativa, quindi a seconda della...
Beh, almeno lui è onesto, sì.
Però in alcuni casi è un eufemismo un po' speculativo, sì, per alcuni aspetti del film. Vabbè, però dai. Cioè, l'immagine del buco nero...
No, quella è vera proprio.
Quella l'hanno fatta, era fatto il suo gruppo, i codici numerica relativity proprio pieno.
Non so quanto ci hanno messo per farla davvero.
State of the art.
Sì, no, assolutamente.
Science. Però certo, poi quello che torna nel futuro, nel passato, eccetera, però lui l'ha cercato sul fatto che non è dimensional, no? Non era una quarta dimensione.
È vero, sì.
Però non mi ricordo, mi sembra che riesce anche un'altra volta.
No, mi ricordo che c'era un sito che faceva tutte le linee temporali del film. Sì, lui entra e riesce.
C'è questo Tesseract che non era normale. Però c'è un articolino che fece Carlo Rovelli in cui mostrava che queste closed time lag curves, che sono bellissime, perché effettivamente
delle closed time-like curves, cioè una geodetica time-like, e quindi questo è un osservatore che è chiuso e quindi è anche detto abbastanza. In realtà, come faceva vedere, finché è di una particella funziona il tempo, ma se tu vuoi qualcosa che sia un sistema termodinamico, perché anche un orologio è un sistema termodinamico, cioè se non è un sistema termodinamico non c'è memoria del fatto che non c'è un paradosso, perché non c'è memoria di dire sono tornati per tempo, a quel punto si perde tutta la cosa della closed time like curve, e quindi in realtà non ci riesce a dare il tempo.
Cioè proprio non riesce a farlo,
E quindi non è il paradosso.
in effetti è vero, se fai semplicemente l'asse tempo,
Sì.
Il punto materiale è una soluzione dell'equazione, cioè, ma non è una soluzione, la cosa che ha affascinato tanti è che non è finché era la soluzione di Gödel dell'equazione di Einstein, era un universo che non esiste, non importa, ma qua sono di Kerr che vediamo che prevedono le cose curse, e quella è una cosa effettivamente che colpisce. Sì, il numero di Kerr prevede le cose nella curva, solo che appunto c'è qui dire no, il wormhole è una cosa diversa, il wormhole
Quello c'è lavori di come si chiama
exotic matter,
problema
ci vuole una materia che viola la strong
energy
energy
conjunction.
condition, che insomma un po'.
Cioè la cosa era qualcosa che regge la gola, che non l'ha fatto là. Mi sa che questo aveva fatto degli articoli Kip Thorne proprio.
I primi articoli sono di Thorne,
però non funziona comunque per Schwarz.
Beh, è un'altra metrica.
No, ho capito, dico Schwarz
neanche quella, no. Però che praticamente la singolarità, invece di avere la topologia di un punto, la topologia di un anello. Se tu entri nell'anello e poi ci giri attorno, a quel punto fai vicino all'anello una geodetica circolare, quella geodetica circolare è time-like, perché praticamente lì GFF cambia segno, e quindi
praticamente ok. È come Schwarz che cambia segno, però non puoi cambiare solo sempre
invece in quel caso ci gira attorno, e quindi
Campanelliamo. Okay, so shall we start? So as I was saying, now we have more or less at least a form of how delta t will appear. So we need to understand which is the form of the h that we need to plug inside the Einstein equation, and the operator then will give us whatever, a set of equations that relates the two. Okay? Now, to understand how we can actually treat the problem, we can exploit the symmetry of the background. Okay? Now, without being too much sophisticated, but basically the point is that you have a spherically symmetric background, exactly as you would do like the second year of the bachelor, so without taking into account GR and whatever. If you have this kind of background, the most common and useful thing to do is expand these in spherical harmonics, which provides a complete basis on top of this spherically symmetric background. Now, here the situation is a bit difficult because you don't have scalars, you actually have tensors, but the procedure is exactly the same. So instead of the usual spherical harmonics, you will have like tensor harmonics, which gives you like a complete basis, but these are still functions of spherical harmonics. So for us, at least for the level of this course, we really don't need to understand the difference. So the basic idea is expand everything in spherical harmonics. so the usual YLM theta. And we will also do in a particular gauge, so we'll also transform this equation, which is in which we can put 4 out of the 10 components of H to 0. So remember that H is symmetric, so it has like in principle 10 components, but I'll make a coordinate choice such that 4 of these die immediately. Okay, so at the end, our matrix will just be given by this form here. So these, remember, as we said before, that must depend on r, theta, and phi. Okay? So the perturbation depends on this variable, The theta and phi are here. So the dependence on the theta and phi, the angles is encoded within the spherical harmonics. So what we are left is I hope that it goes in the blackboard. Let me write and then I'll explain you all terms. So the metric perturbation will depend on these components, these coordinates are theta and phi. The angular dependence is encoded by the spherical harmonics. As I said, we transform everything in the Regge-Wheeler gauge such that only 4 perturbations, only 6 perturbations are relevant. So 10 minus 4. So there are only 6 left. Nu and F are of the background, so they're already known. And then, so here, you see at the blackboard, there are only 4 perturbations that we need to solve, 4 variables that we need to solve out of these. So there are 6, and of these you find that the only thing that we need to try to solve is H0, H1, H2, and K, and all these functions depend on R. Now, as I said, there are 6 only degrees of freedom, okay, here, and because we have killed 4 with this gauge transformation, this Regge-Wheeler gauge transformation. For the calculation of the L equal to, I've put here the sum just to highlight the point that when you decompose everything is spherical harmonics, you have a sum in different multiples, so in L and M. But for us, as I said at the beginning, so each L will correspond to a different tidal deformability that we said we discussed yesterday. So the lambda 2, lambda 3, the octopolar deformation, and so on. Okay. I just put here for clarity, but for us, as I said, since we're interested only in the quadrupolar leading term, this sum collapses to L equal to. There's no infinity. We will have only one term, okay, which is the L equal to. You may ask, what are the other 2 components of the 6? because that matrix there, I mean, in principle, should have other two components. Well, I cannot go too much into this, but after this Regge-Wheeler gauge, as we saw yesterday, there are two families of tidal deformability, the mass and the current, okay? And these four will belong to the mass, so the mass tidal deformability will be determined by these four. There are other two components of the metric which determine the electric tidal deformability. Now, when the background is spherically symmetric, the two don't talk each other. Okay, so basically I haven't included them here. So for the calculation of the mass moments here, and in particular of the L equal to, the other 2 degrees of freedom of the perturbation, which would determine the electric tidal moments, do not matter because they won't couple with this variable, so I just remove it from the blackboard. But just keep in mind that, again, there are in principle 10 components of H mu nu. I kill 4 of them because I want to, I use this gauge transformation, and I've been left with 6 perturbation, okay? Now, the physics doesn't really distinguish between electric and tidal moments in the sense that I compute everything, but since the background is spherically symmetric, these two things won't talk each other, and I can treat them, and I can actually compute them independently. So for this problem that we are discussing now, there are only 4 variables that we need, which are those there. Out of these 6, there are other 2 variables that belong to this problem, and they will not talk with this. So if you want to solve this problem, you can basically take that matrix with only the remaining 2 components and solve all those equations independently. Okay? Only of R, yeah, depending on R. Yes. Okay. All right. So this is the decomposition of the metric tensor in spherical harmonics, but we also need to, we have expanded delta T mu nu in a perturbative fashion, so we have actually highlighted linear terms, but we also need to expand now everything is spherical harmonics, because I mean we are expanding both at practical level, both the left hand side and the right hand side on this spherically symmetric background. So we have expanded these in what I said are like tensor harmonics, which then basically are just proportional to spherical harmonics. The density and the pressure perturbation are scalar per se, so basically they can be expanded straightforwardly into scalar harmonics, so the one that you already know. And so you can basically expand them like this. Delta P where delta epsilon and delta PLM only depends on R, and of course the Y depend on the angular variable. And then the last thing is the delta U. For the mass moment, the only thing that we need to care are perturbations of okay, that's it. So let me write here a summary of what we are doing. We are computing linear perturbation on top of a spherically symmetric background. I'm using this property of the spherically symmetric background to expand everything in, let me write this in basis of tensor, vector, and scalar harmonics. Scalar harmonics basically will take care of delta E and delta P. The tensor harmonics will take care of H mu nu. And we haven't seen, but the vector harmonics will actually take care of the only vector that we have left in the game, which is delta U mu. Now, okay, I've made these like in 2 lines because we don't have time. But at the end of the story, everything reducing or having like a sum of spherical harmonics on the left, a sum of spherical harmonics on the right, okay, for each Einstein equation. Okay. Since the spherical, the background is spherically symmetric, again, as I was telling you before, the 2 sectors of the Taylor number don't talk each other, so you can compute them independently, and also different harmonics with different L don't talk each other, which means that you'll never see an equation which has, I don't know, delta epsilon 2, 0, and delta epsilon multiplied by delta epsilon 3, 0. So L and L plus 1, L minus 1, or L plus 2 will never couple because of the spherically symmetric background. So you will always have that only terms with the same angular dependence, which also basically means that I can really completely get rid of the sum, because I just have an infinite set of L equation on the left-hand side and L equation on the right-hand side. Now, to make even more simple, in the sense for us, we are really looking at the L equal 2, and we are fixing this, and that's it. Okay? If the background was spinning, this wouldn't happen, and actually the multiple moments with different L would actually mix together, so you will have selection rules, and I mean, everything becomes way more involved. And finally, since the background is spherically symmetric, basically you can imagine that the M number, which basically describes the rotation under phi, doesn't really matter. Okay, and indeed, if you actually develop all the equation, even if you keep the M, because the spherical harmonics, Y, will have this factor, right? Okay. Since for us the background is spherically symmetric, that factor won't matter. So you can, if you really want to do everything keeping that, you can do it, and at the end of the story we will see it will simplify. Okay, so I'll take it M equals 0, and that's it. So everything will be even easier. Okay. I can further simplify another bit my solution or my problem, because the perturbation in the energy and the pressure are not really independent, but I can define a speed of sound in the usual way, such that delta E and delta P, or delta epsilon, sorry, and delta P are related to each other. Now, we're going to do tomorrow, we're going to literally click on the Mathematica notebook and find what I'm showing you today. I just want to give you the sketch. But at this point, we have everything, so we can just plug everything inside the Einstein equation. Let the operator of the Einstein equation basically means letting first and second derivatives acting on all the spherical harmonics, the radial components, and element by element the Einstein equation, you will find a set of differential equations that we need to use in order to find a solution. Now, if you expect the Einstein equation, you're going to find that there are relations between these 4 variables, okay, which simplify the problem. And in fact, one of the Einstein equation just tells that H2 is equal to H0. Okay? I'm not putting indices here, okay, because we are working on L equal to M equal 0. And we know that the sum doesn't take mixed terms, so I mean, we don't care about this. So one of the Einstein equation, again, we're going to see tomorrow, just tells us that two variables are related to each other, but also tell us that delta P is related to the background energy and pressure density, the N d H naught there. Then K of R can be expressed as a generic function of H0 of R. So again, H2 becomes equal to H naught. Delta P can be expressed in terms of H naught again. And there is another equation that gives K as a function of A naught. And then if there is another Einstein equation that sets H1 equal to 0. So at the end of the story, thank God, there is only one variable going around, which is H naught. And indeed, this problem that looked a bit messy from the beginning reduced to solving a single differential equation. It's actually an ODE, because the background is spherically symmetric. And so you get an equation for H0. The double dot means double derivative with respect to R, because this is the only thing. I'll just write everything at the blackboard, because then I'll need it to show something. You really don't need to copy this, I mean, it's irrelevant. I just want to show you that at the end of the story, you get a second order equation for H naught, and everything which is inside the square bracket is known, because everything that is inside here is basically background. Okay, so in principle, when we have solved the G mu 0, we have computed M of R, the P, this is and epsilon are specified by the equation of state, the derivative of nu is defined at the background level, F is defined, so everything is based known. Okay? So at this point, we just need to solve this thing numerically, and then do actually the game that we discussed yesterday, because all of these will give a solution of the metric perturbation inside the star. Now we need to integrate from the center of the star to the radius, as we have done for the background quantities, and then do the matching at infinity and blah, blah, blah. And this is something that we're going to do now. Okay, but first, let's do the integration inside. We need to integrate this from the center as we done for the mass component in the background. So I need to find starting condition for H naught at the center of the star. Yes, tell me if you have a... Where? 5 epsilon. Plus epsilon plus p divided by the p in that thing, the speed of sound. Plus 9 pressure. Sorry. You're welcome. Okay. So I need to find a condition at the center. And if you take that equation there, and you literally make a Taylor expansion for R that goes to 0, you're going to find that these things goes as A naught r squared plus O d r4. So it goes as a constant times r squared. Now it turns out that this constant is totally irrelevant because at the end of the story, the solution, so the log number, or the tidal deformability, actually let's write as K2, will be given by H0 divided by H0 prime. So, or the inverse, it doesn't really matter, just ratio of this function. So constants here and here will simplify. And indeed, in the numerical integrator, you see that if I choose this 1, 1,000, and 10,000 million, it's not going to change anything. Okay? So the solution, just to say that you have to integrate again from the center of the star to the radius, okay, with some values of A naught. And since you only have one equation, I have like that I can integrate that equation there, imposing H naught equal to 1 r squared at some values that for me is the center of the star. And then it's a second order equation, so I need another condition, which is H naught prime, so 2H0R, and that's it. And I integrate up to the boundary which I found when I solved the background solution. Okay? Okay, now it comes the matching part. So let's assume now that I have my solution, which is H0 var determined, and we're actually going to determine this tomorrow. And now I need to develop my solution at the radius, compute it, and then match these up to infinity when I can make basically the equation between H naught, or if you wish, the GTT that I get here expanded at infinity with the asymptotic centered mass Cartesian blah 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 frame that we've seen yesterday. The first thing that I want to do is compute the solution at the boundary of my star, which is R equal capital R, the radius. Remember that the pressure and the density vanishes at R equal capital R because we are in vacuum. So basically, we can find for R equal capital R an analytic solution to that equation, because if you take that equation there, that's valid for any value of R. But at the surface, which basically means in vacuum, you can kill all terms that contains matter variables, and the metric function e to f and e to nu will collapse to the Schwarzschild value. You see, do I need to write this at the blackboard? So this will go to 0, and then e to nu will become 1 minus 2m over r, and e to minus f will be 1 minus 2m over r. Okay? This goes because the exterior is a spherically symmetric background, so it's going to be dictated by Schwarzschild metric. So I plug this there instead of e to nu and e to f. I kill everything which is p and epsilon. And if I plug this in mathematics, I'm going to find that there is an analytic solution for that equation in vacuum. And this analytic solution has a very nice form in terms of Legendre polynomials. So H0 for R larger equal to R has this form. P22 and I guess it's Q22 are like generic solution of the R Legendre polynomials, function of R, and capital M is the mass of the star, plus I have two constants of integration. Now, basically, all the physics that we are looking for is in these constants of integration. Because now, what you have to do is, you take this solution here, and you plug this into the GTT, our starting GTT, because we wrote our metric G mu nu as G mu nu background plus H mu nu. What I want to do is, I don't know how many sketches I can do, but at infinity, where I can extract my multiple moments, I have my metric, GTT, that we've written yesterday at the blackboard. Okay? Remember that that metric in particular has a 1 over r cubic dependent part, which depends on the quadruple, and then an r squared term, which depends on the tidal tensor. Okay? Then I've integrated my h naught of r from here to the boundary. Okay? At the boundary, where there's vacuum, I found that h0 of r, sorry, capital R, is given by this value there. Okay? So what I need to do now is take the G00, and my G00 will be outside, let me write it, R larger equal to R, will be minus 1 minus 2m over R plus this thing, plus something which is proportional to H0 of R. Okay? Remember that I cancel, but so if you take the full metric, so the G0, the G mu nu 0, plus the perturbation that we've written, the matrix perturbation that we've written on the blackboard, you can just extract the G00 component. Okay? Or the TT is the same. Okay? And this is completely analytic. So now, I take this metric which is valid outside the star, and I make a limit or a Taylor expansion for R that goes to infinity. And then I match this solution with this thing here. Now, if you take this expression of the metric, so the Schwarzschild component, plus this thing here, and you take this thing, and you expand this for large R, you're going to find that this, so our GTT R that goes to infinity is minus 1 plus 2m over R plus 8m cubic 5 cubic CQ plus 3r squared m squared CP CQ to 0, C to 0. Okay. So what I've taken again is just this value. Remember that the perturbation, besides the radial function, is also a dependent on the spherical harmonics. So I've taken the metric function, the G00, and I have expanded this at large R. And at large R, it has this form here. This CQ and this CP are just basically related to this constant of integration. I just called slightly with a different names because there is a rearrangement of factors, other numbers that comes from the fact that I expanded infinity, but they're basically the same. Okay? And as you see, in the metric that I'm expanding at infinity, now there is this character of decaying function and growing function that is emerging, and this is exactly the character that I want to match between this and this. Because then, I take this metric that we wrote yesterday at the blackboard. There is one very little ingredient that I need to do. This metric yesterday, if you check on the blackboard, was written in terms of generic quadruple and tidal tensor amplitude. I just, since I've written everything in spherical harmonics, we can expand also this in a basis of spherical harmonics or tensor harmonics. Okay, so now this G00 GTT SCMC that you have on the notes will just take this form. Where I expanded the generic Qij that was in the metric in this way. QLM, actually, yeah, Y. I know that it looks very weird, but I mean, that's it. So I just basically written like the generic QEJ in terms of some functions which are just related to the usual spherical harmonics. So the usual spherical harmonics are the projector of this function here on top of n, which is the unit vectors, basically. This is Ni is xi divided by r. But the basic idea in any case that I am expanding this in spherical harmonics with these amplitudes here. And these go there. Okay, I think at this point we have done everything, because now we can immediately relate this and this and this and this, which are the two things that we are interested. Because without this procedure, we wouldn't know which part of this thing corresponds to the quadrupole and which to the tidal field, but in this case we know that this guy here is actually related to the quadrupole moment of the source. So now we can write the two constants of integration in this way. We're almost done in the sense that we have the quadrupole moment. You may ask, where is the tidal love number, the tidal deformability? It comes from what we defined at the beginning as the adiabatic approximation. So when we started yesterday discussing, we said that in the weak tide approximation, the tidal induced moments were related to the source of this moment, so the tidal field, at the linearly. So basically we said that those Q over L was lambda L, we call it GL, or epsilon L is the same actually, yeah. We call it this in the way that we written yesterday, G. Remember that this was the quadrupole, so the tidal induced moment on the stars, and this was the tidal field, okay? So for a quadrupolar thing, this was this. And so this, replacing this, you actually find that this is 5, 8, like this. Now everything is done in the sense that we have basically something that depends on the love number and is related to our this is G. So we have now two constants of integrations, which are fully determined, because these constants of integrations let me say this for the last time. So we said that basically we integrated the H0 of R from the center of the star to the boundary, and at the boundary the function H naught of R depends on this CP CQ. Okay, now what I can do is numerically integrate H naught here, then compute the numeric values of H naught and H naught prime, compute this thing at the boundary, and because my solution must be continuous, I actually just take an algebraic relation that gives me, let me then use this thing, the numerical values that I compute at the boundary, so for R equal R, of the first derivative of the function, and I match it with the analytic solution. And from this numerical, algebraic numerical matching, I find the CP and CQ. Okay? So this CP and CQ will depend on the numerical values that I got integrating inside the star and evaluated at the surface, because I need continuity. My solution needs to be continuous all over the domain. Then I have CP and CQ, which are determined by my background quantities at the end, so by my initial choice of pressure, density, and blah, blah, blah. And I can plug it there, because those constants are fixed by these values. And I have actually an analytic solution for my love number, which of course I don't want to write at the blackboard. Where is it? Why is it not showing? Which is that one. Vabbè. Which is this one. Now this is the love number. So basically, because if you see the love number here, so you can basically get G2 from, so the component of the tidal field from this value of the constant. You can take, and then everything is determined because lambda 2 will be given by these constants and these constants, which I get from these two values. These two values are inside, fuck, I forgot to write, are inside Y. So Y is H0 prime R divided by H0 of R multiplied by R. In the way that I've written it is numerical. So the love number there is then determined by these numbers that I find integrating the perturbation inside the stars. And again, let me say that these are given because I'm matching this solution with the external values. And then the nice thing is that this analytic solution depends on the compactness of the object, so of the star. And as you see there, the compactness is just the ratio in geometric units between the mass and the radius of the star. This, if you then compute the love number here as a function of the compactness, you find something, something that is obvious and something that immediately comes out from this equation, that probably is a bit less obvious. The first one is that the love numbers decreases, take only, these are all basically, each of these lines corresponds to different stars, and each colored line is a different equation of state. It's a different view on the mass radius profile. Instead of masses and radius, I have the compactness, the love number and the compactness. And as you see, the love number decreases as the compactness increases. And this is very natural because, if the object becomes more and more compact, it becomes more difficult to deform it. So you would expect that the love number, which describes the magnitude of the deformation, becomes smaller and smaller. But there is also another interesting point that if you take the limit of this expression for C, for the compactor that goes to 1/2, which is the black hole limit, so like a Schwarzschild black hole has a m over r, which is exactly 0.5, the log numbers goes to 0. So black holes are indeed the most rigid body as we consider in the universe because they are not tidally deformed, because their response is equal to 0. Now, all of this is actual in the sense of real physics because these log numbers, actually, the tidal deformability, so the log number multiplied by the radius, have been measured by Lag and Virgo, and indeed these are like contour plots, so these are the posterior distributions measured through the first binary neutron star events, okay? And these are the masses of the stars, and these are like the two log numbers measured by Lag and Virgo. And what you see here are like density distribution, so the posterior densities, like where you see stronger colors, it means that the values are more probable. And for lambda 1 and lambda 2, so the log numbers of the two stars. And if you see these black lines, these are predictions of log numbers for certain equation of state. So you take an equation of state, for example, one of that in these colors, these colors here. And if you use the values of the masses that basically they found for this event, they will predict log numbers of this kind. So this plot shows you that you can use actually log numbers to constrain the parameter space of the equation of state, because basically here is the region where the probability of having like the log numbers is the highest, and then it's fading, I mean, as you go to larger log numbers. Okay? And in particular, this white zone is everything which is excluded at more than 90% convenience level. And so this plot tells you that all the equation of states that are in the white region are excluded by these measurements. And actually some of these are very alike, in the sense that are in the low probability region. Now, the name of the equation of state don't really matter, but what it matters is that the measurement, or at least this measurement that we have done, seems to suggest that large values of the log number are a bit excluded by this observation. Large values means large tidal deformability or less compact objects. Okay? So this measurement here tells you that we expect, to at least the first binary observation, suggests that neutron stars are very, very compact and are compatible with the equation of states which predict compact sources. Okay, so what we discussed last time as stiff equation of states, so something that with a given radius predict very large radii, is actually excluded. Okay, so at least this observation seems to suggest that neutron stars are compact, and the equation of state that predict fluffier, so more deformable stars, are actually excluded by observations. Okay, in the last 10 minutes, I actually want to tell you that log numbers have actually become, in the last years, a tool for testing general relativity because of one of the last things that we have seen on the slides, and that log numbers vanish for black holes. Okay? For black holes in vacuum GR. Okay? And this is not only true for Schwarzschild, so for the static limit that we've seen here, but there have been like a series of work that has shown that even if you take a fully Kerr rotating black hole, so a Kerr black hole fully rotating, the log number will vanish. Okay? But the log number do not vanish if you have black holes beyond general relativity, so there are modified theories of gravity, okay, in which you have black holes with airs, and in some of these theories predict that the log numbers are different from 0, or there is a plethora of models which goes as exotic compact object of black hole mimickers. These are mostly like high energy or quantum inspired compact objects that basically are trying to model or to develop solutions which are as compact as black holes but don't have an horizon. So there are like suggestion of like solutions for compact objects which may solve like singularities or things that people don't like to have around, and wormholes like to be very movie addicted, and some of these objects have non-vanishing log numbers as well. But also, if you put black holes with some matter around, it will develop a non-vanishing log number. So if I have like a black hole surrounded by an accretion disk, or I have a black hole surrounded by a dark matter halo, and if you compute the space-time metric, then the log number will be different from 0. And then you can imagine the kind of experiments that we can do. You measure a binary system, you are 100% sure that your masses are at least larger than 50 solar masses, I'll give you the number, and you are 100% sure, of course it doesn't realize in nature, but I mean just to make an extreme, that the log numbers are different from 0. So you have two objects which are very, very massive and have log number different from 0. So you either haven't understood anything of stellar evolution, so there are compact objects like stars which have masses of 50 solar masses, or you're looking there at something which is different from a black hole in vacuum GR. Now, measuring at 100% surely that the log number is different from 0, of course, is an incredibly difficult game, but I mean, in principle, it's something that can be done. And yeah, let me give just a couple of examples for these log numbers in things which are different from black holes. These are, for example, like two cases of exotic compact objects. One are boson stars. So these are basically solutions in which you have a scalar field which collapses and form like a self-gravitating object. Is defined by this Lagrangian here, this action which like the fine details of the structure depend on the kind of potential that you choose there. And these objects actually have, at least some of these objects, some of these configurations, this boson star, have predict log number which have a behavior very, very similar to those of the neutron star. And this, for example, like the log number as a function of the maximum mass, and they decrease as the values of the mass increases, exactly as you would expect for a neutron star. If you take a boson star with a compactness of 0.2, so an m over r of 0.2, and you take a neutron star with the same compactness, this is the kind of values that they predict. Okay? So they predict basically log numbers which are a bit smaller than those of typical neutron stars. And this is a plot instead of for very fancy objects. So if these are really what they call in jargon, in literature, are called like black hole mimickers. Black hole mimickers are really objects that would be very, very, very compact and like close to a black hole. So something having not a compactness of 0.5, but something with a compactness of 0.999, something like this. Okay, which have like deformations from what would have been the horizon of the order of femtometers or whatever is the small length. So in which basically these are stars in which there is a surface instead of at the horizon, which is shifted from 2m plus a delta. And you see how basically the log numbers, the values of the log numbers as a function of this delta in centimeters. Now, it appears that for many models like this, the log numbers scales logarithmically with delta, which is very, very good in terms of observation, because even if you have values of delta which is very, very small, like 10 to minus 20 centimeters, this means that you have a star with a surface which is 10 to minus 20 centimeters from what would be 2m, so an object with an horizon, exactly the same mass. And these have like values of the log numbers, depending on the particular model, of the order of 10 to minus 1, 10 to minus 2, which is not dramatically small if you try a bit to balance with intuition the fact that you are trying to observe deviation at this level in terms of distances. And nothing, I think that this is probably the last slide and I can close. I think probably the best observatory in terms of gravitational wave bandwidth in order to constrain log numbers is LISA. LISA is this future satellite that going to be launched in 2035-37, and in particular, we will observe a particular type of systems which is deemed to current detectors, which are like asymmetric binaries. And so in particular, this is a sketch of one of these extreme version of asymmetric binaries, which is the extreme mass ratio spirals. As I probably mentioned in some of the the slides or the discussion that we had, an extreme mass ratio spiral is a binary system within which there is a very massive central object, let's say 10 to 6 solar masses, and then a small guy of the order of 10 solar mass, let's say a stellar mass object, going around for tens of thousands of cycles. And this is the smallest values that you can measure of the log number of this guy here. Now, LIGO and Virgo have basically put a constraint on the log numbers of the order of 100. Okay, so the log number must be smaller than, on the tidal deformability, not on lambda of the order of 100. Now, in these units here, K2 is equal to lambda. So you see that with Lisa, you can measure the log number of, or the tidal deformability of the massive object at the level of 10 to minus 3, 10 to minus 2. This is basically gives you the smallest values of the log number that can be measured as a function of the black hole spin. And you see that if you increase, more faster is the rotation of the central black hole, better you can do your measurement. And in particular, even like for the 07, 08 spinning black holes, which are not dramatically large values of spin, look at basically you get values of the order of 10 to minus 2. Okay. Now, these numbers here are compatible with the mimickers, okay, with basically these values of K. So basically Lisa would be like the perfect observatory, and in particular Lisa supplied by observation of this kind of system to constrain log numbers of this order here. LIGO and Virgo and even the Einstein telescope won't be able to, will be able to do physics, but in this kind of scenario, but the very best will probably constrain this kind of compactness and log numbers. So we'll constrain log numbers for boson star, something which deviates from neutron star, but is not as extreme as a black hole mimicker. Okay, I think that that's it. I'm gonna release this slide so you can find here some references for the topics that we have discussed. And tomorrow we're gonna I'm gonna actually want to give you a brief, because we basically discussed about gravitational wave emission, so the very early part, or like a general part, in which if you then put these into the spiral sketch, the quadruple just give the very early spiral. Then we jumped immediately into the tidal part, which is the last spiral phase. I just want to give you a sketch from the ring down, and then we'll do the hands-on session mathematical. So please, if you have time, download the files that you're gonna find. So at least tomorrow morning we don't waste time in downloading it, and you have it ready for click and play. Okay, that's it.